Welcome to a lesson with Dr. Powell. Let's take a look at another way of thinking about matrix multiplication by rows instead of columns. In particular, let's think about this right here. So what is this? This is a matrix function. This is a matrix function, but these are A, B, and C. I let this be parameters or whatever. But if you fix some values of this would definitely be a matrix function. And you first run this matrix function if we're doing columns, and then we do that one. Okay, so, but I let these be variable, and for a reason, because if I change their values, I would get a different function. So I have two different functions. Let's think about what that is, like f and g, and maybe one is represented by certain values, and the other one's represented by other values. And if I add them together and I input something into them, like this is outputting things, and then I put those into there. Now notice that inputting something into those is the same thing as inputting this into both ones and then adding the results, like f of v plus g of v, right? So, which is interesting because I could think about a v input function or an evaluation function at v. And what I'm inputting is functions. And what if these functions were vectors themselves? This would be an additive function. In fact, it's scalable as well. It's actually a linear transformation. So if my functions themselves actually look like regular vectors, like maybe a row, that looks like a single vector right there. What if it was like a row like this? That would be like a vector. So this is actually a linear transformation, and it works equally well. And what I can think in this term, in this way of thinking of this as being like E1 as being like 1, 0, 0 as a row, E2 as being 0, 1, 0, and E3 as being 0, 0, 1, 3, 3. And this is a linear combination of these guys, and I could think of where these are being sent. And in terms of linear transformations, it works perfectly well. And you get the same result with matrix multiplication this way as you do in the column interpretation, meaning that this is the image of E1 as a row. This is the image of E2 as a row. This is the image of E3 as a row. And you can even check that. I mean, think about this. If you have like 1, 0, 0, and you have this, you have 3, 1, 2, and you have other stuff down here. Think about what happens. So we have whatever here and whatever here. So we in the column interpretation, if you put this into here, we have 3 times that, and then we have like this times 0 and that times 0. They don't do anything, right? So it's only like you have doing 3 times 1. So you end up getting that. So what we end up getting in the result of inputting this, and notice that the codomain is R, is we just simply get 3. And similarly here, you'd get 1, and there you get 2. So this picked out the first row. So E1 is sent to the first row. E2 is sent to the second row. E3 is sent to the third row. So this is a row interpretation of matrix multiplication. It works just as well. Let's look through an example. So what if we had something like 1, 2, let's see, 1, 2, -1, and we'll do something similar. So 1, 2, -1, and so thinking about this, okay, since we're running the other way, let's think about what this means. The domain, so we're going this way, right? Okay. So it looks like this guy right here, we're inputting it into here, and we need to know where this is traveling. And if we go this way, let's see. Well, in the column interpretation, let's just stick with that for a minute. The codomain is R, and the domain let's see, what's the domain of this guy? The domain of this guy is R3, which means that the codomain of this guy has to be R3, and we can do anything else we want. So we could have a 2, 1, 0, 1, 1, -1, and that should work just fine. Since we're going from R2 to R3, which goes to R. And that is just fine. Okay, now let's see what happens here. If we're thinking of this as a vector and we're inputting it into that, right? We're just taking a vector here and we're inputting it to that. And this vector right here lives in R3. So I guess if you're looking backwards, I mean, since we only have one vector, it's as if we took an element of R like 1 and we sent it to this, going back the other way. And then we take this element of R3 and it's going to, what is it going to output? It's going to output something in R2. Why is that? Well, think about what all the images are. The image of E1 is something in R2. The image of E2 is something in R2. The image of E3 is something in R2. So what we do for columns looks like you do it in exact reverse for rows, for the row map. Okay, if we're having a row interpretation. So basically what we do is we say 1 times the first guy plus 2 times the second guy plus -1 times that guy. So it's like 1 times 2, 1. And then we have 2 times 0, 1. And we have -1 times 1 minus 1. So we end up getting 2, 1, 0, 2, -1, and +1, and then we add. So we had 4 and 1. So we get a 1 and 4 right here, and that's okay, right. So we get 1, 4, and that's the result. So we just did the matrix multiplication, and we got out something in 1, 4, because we're thinking of this as a vector. This is the input vector in R3, and we output something in R2, just like this matrix said we would. We outputted something in R2. And notice that if you thought about this as being a function in and of itself, going this way, then this works perfectly fine, because what is the, this works perfectly fine because the domain is, so everything's flip-flopped. The domain now in the row interpretation is the number of rows, and the number of rows is 1, meaning the domain in this case was R. And notice how the number of columns is 2, so the codomain would be 2. It's flip-flopped. So it goes from R to R2 just as expected. So this is perfectly valid if you think of it that way, or if you just think about plugging in a vector, it works as well because it's in the right codomain. Thanks for watching.